I have to begin with a few prefacing remarks today, so a couple of apologies. First of all, I apologise for looking absolutely nothing like my photograph in the brochure. If it's any consolation, this is how I always look. The stuff in the brochure was completely airbrushed. I wore a tie once to get married, and I met Prince Charles once, and they wouldn't let me in without a tie on. Those are literally the only 2 times in my life I've worn a tie. So that one is airbrushed on. I am a bit complicated. I'm a professor of engineering at the University of Sydney. My uni lab, I grow gold on trees and reverse engineer butterflies and do really unusual futuristic stuff like that. But I also have a couple of other roles. I sit on the board of the Australian Government's Research Centre for Robotics and Computer Vision. Have a couple of startups that I've done in my life. One of those is Hazer. It's a little listed clean tech on the ASX. I'm a non-exec director there. And then I have a role that I've been doing for about 8 years now with a little company called Langer Rourke, who are a design, engineering, manufacturing, construction company headquartered in the UK, but who've been working in Australia for near on 40 years now. So most of what I'm going to talk about today is focused on my work with Langer Rourke, if that's all right. We'll see how we go. All right? You can all hear me, yeah? Great. Okay. So I promised to talk about, this is my second apology, sort of robots, 3D printing. I think we were going to grow some buildings, which we'll do at the end. Actually, what I'm talking about is disruption. So quick primer on disruptive innovation. So quick primer on innovation. If you ask a business school professor, they'll talk to you at great length, probably for 8 or 9 days, explaining what innovation is and how it works. I actually don't think it's that complicated. In my world, there are 2 types of innovation. There is disruptive innovation and incremental innovation. So incremental innovation is doing what you did today, tomorrow, a little bit better, right? That's everybody's job every day. Yeah? And then there's disruptive innovation. That's holy shit, I didn't see that coming, I don't have a job anymore. So my job is the disruptive innovation piece. So I'm going to largely focus on disruptive innovation today. Don't worry, most of your jobs are extinct already, you just haven't sorted it out yet. I'm going to focus on survival. I'm interested in business survival, but actually this is more important than that. It's essential for Australia's survival. Particularly topical at the moment. I think we're about to have a changeover of Prime Minister. Maybe not, maybe it goes back again. Dear Lord, it's a mess. So I am going to use engineering and construction as a case study for disruptive innovation. So those of you in the industry in the room might be thinking that's a little bit risky. After all, we still build buildings today the same way the aliens built the pyramids 5,000 years ago. Like, it literally hasn't changed. So if you think back to my definition of disruptive innovation again, can you name me a disruptive innovation in the construction space since the invention of the brick? Right. So maybe concrete. So that's a Roman invention, that's about 700 years old, right? Perhaps structural steel, but I think that's incremental, right? Because it's just a structural element that's made from a different material, it does the same thing. Perhaps glass, probably not, right? I cannot think of one, and I try really hard. So, but you'll see there's some really interesting stuff going on. I'll share with you some examples. I hope you see where we're getting to. I do want to make some brief observations about the importance of universities, education in all of this. I'm a deeply passionate educator, and the university sector in Australia gives me the screaming shits. And we can talk about that at length again, if you like, at the end. And then I want to talk about your careers, or lack of them, as we go through. This is always much more fun for me than it is for anybody I'm talking to. So let's see how we go. And there'll be heaps of time for questions at the end. Okay, so the first thing I want to do, I want to show you some pictures of my lab, if that's all right. I do what is known in the field as translational research. So very, very cutting edge stuff, and then I try and find places to apply it. So my lab, and these are some of Langer Rourke's projects around the world, as commercial buildings. I have a big resources business, that's Cape Lambert. It's Rio Tinto's primary iron ore export facility in Australia. It contributes about 3% of Australia's GDP. And Langerook's built most of what you see there over the last 30 years or so. Oil and gas, Wheatstone is Chevron's, very, very big. In fact, this was the biggest construction project in the world for most of the last 10 years. Topped out at about 80-something billion dollars. We had a little civils package in the middle there. It was about a $3 billion concrete slab. And I'll show you the BIM model for that in a bit, actually. Most folks wonder why we would do a model of a concrete slab in digital engineering, but you'll see why. We have a big rail business. There's a bunch of level crossings been removed in Melbourne here. NEPA, the Northeast Program Alliance, is one of those. We're finishing off the completion of the Pacific Highway in northern New South Wales, the duplication of it. This is the largest regional construction project in Australia at the moment. And this is interesting for us because we do no construction. We are simply, with Parsons Brinkhoff, Jacobs, we are managing, I got that wrong, WSP, my bad. We're managing the construction of that. So this is the poacher turned gamekeeper model, right? Most of the risk in a project comes when you're spending the money. But most of the ability to influence that happens at the design phase. So this is about getting the construction smarts earlier on in the project. And this was a model that we pioneered in the UK with the London Olympics. Again, we managed that for the with others, but sort of £8 billion worth of work, zero construction for us. We do a little bit of tunnelling. Again, our rail business in the UK, there's an extension to the tube in London. That's Battersea Power Station at the back there. The tunnel boring machine I showed you on the first slide is Helen, and Helen's one of the two doing the Northern Line extension. And they broke through earlier this year. So it's a joint venture with Murphy's, who are a little Irish-English contractor, Anglo-Irish contractor, and Ferrovial. So I'm a chemist and a chemical engineer by training, a long time ago. So the butt of most of my jokes throughout my career have been civil engineers. It's obvious why, right? That was a joke. It's easy. Calm down. There's a lady in the third row who's steaming at the moment. This is going to be a bad day. This is my favourite hole in the ground. This is one of the most complex projects I've ever been involved with in my career, right? So underneath that, it's the 901 project, it's the convention centre in Hong Kong in Kowloon, is that hole. And what makes this so extraordinary is behind the hoarding at the top of that, there's a live railway line with a train every 15 seconds in peak hour that goes through, right? They didn't stop the trains to dig the hole. And that rock is the hardest rock anybody in Langerook has ever come across, right? It's the middle of an urban area. You're only allowed 1 wheelbarrow's worth of explosives per day. So an extraordinary project. And my Mandarin is not great. But those two signs at the bottom of those two props, pretty sure it says, "Don't knock this with an excavator." Because if you do, that's the end of that. So, right. We have a version of this photo with a 747 in it, which I use when I talk to school kids, and bless, they all think that we managed to fly the plane into the cabin. So there's hope for humanity yet if kids have that level of creativity. So we do airports work. If you've been through Heathrow, we did Terminals 2, Terminal 3, and Terminal 5. Another interesting story, the new Queen's Terminal at Heathrow, the one that's just opened, it's either 2 or 3, I can never remember. My job at Langerook's headquartered in the UK, so I travel there a lot. And I was there a couple of weeks after it had opened. I said to the, I'm Australian, 5 a.m., you're in the queue, finally get to the immigration guy. I said, how do you like well, he said, what do you do, an engineer? What are you here for? Some meetings, work, who do you work for? I work for Langerook. He said, who are they? I'd never heard of him. I said, well, this is one of ours. Do you like it? And that was a terrible mistake. 3 hours later, I'm still in the queue having a chat with this guy trying to get into the bloody country. Turned out the issue was the tea room was too far from where he was working. Right? Bless the English. So we also do lots of work in social and economic infrastructure. Again, a job where we do no construction, but the refurbishment of Sydney Opera House. An incredibly complex building, particularly around services. I'll share an example about that a bit later. I mentioned the London Olympics, the Paralympics, again, the program management approach. Zero construction there for us, just managing the workflows, all run from a digital model. And we have a big-ish defence business. Lots and lots of projects around Australia. This is my favourite picture of that. It's the big kahunas in at Amberley Air Force Base in Brisbane. All right. So those are my labs, photos of my lab. I hope you enjoyed that. Back to the stuff at hand. I want to talk about disruptive innovation. I want to use construction as a case study for that, and this is the reason why. In Australia, construction is about 8% of GDP, contributes about 8% of GDP. It's a bit higher at the moment. There's just work going on all over the place. But when you include upstream and downstream supply chains, so design, engineering services, manufacturing, asset optimization and maintenance at the other end, it's almost 20%. It is the biggest single contributor to GDP in this country, and indeed most first world economies, that there is, right? Mining, education and farming are all miles less than that, 7, 8, 9, 10%. Right? It's the third largest employer in the country, and it is the largest employer of young people, where unemployment rates are highest, right? It's the single most important employer of young people, and has a reasonably challenging OHS record. It's by no means the worst, but it's not great, right? People die at work. That should never happen. It should never happen ever. It should never happen again, and unfortunately it does. So it's a really interesting place to look at disruption. All right, so this is my only. This is really bad for me not having a lapel mic. I like to wander around. I'll try not to do that, so you won't be able to hear me. This is my only academic slide. It's the only time I'm going to pretend to be a university professor today. This is data put together by some clever investment bankers. Sorry, that was a joke as well. I should never talk early in the morning. Should all go and have a double espresso, and we'll start again. What they're doing is they're plotting super cycles. They're plotting super cycles in this particular case, the US share market, right? So they're looking at super cycles of growth, and then the opposite of that, over the last couple of 100 years, right? So this is where you've had massive periods of growth, and they correlate those to technological revolutions, the steam engine, textiles, the transcontinental railway in the US, petrochem and electric engineering revolutions, the automobile, the IT boom in the 70s, right? So my point of showing you this is we are due another one of these. These are called Kondratiev curves. This is called a Kondratiev cycle. We're due another one of these, right? So then the question is, in fact, we're overdue, well overdue now, right? So then the question is, what's going to cause it? What is the technological revolution that will bring about this epoch of growth? Is it nanotechnology? Is it biotechnology? Is it digital? The Internet of Things? I've got no idea. And anybody who tells you that they know what the future looks like is some people call them futurists. I call them liars. In reality, it's probably going to be a combination of all of those things plus a whole bunch of stuff we haven't thought about yet, right? But I agree very strongly with Warwick's one of Warwick's points in the earlier slide. The future is already here, but it's just not evenly distributed yet, right? Think of an Ebola outbreak. It doesn't kill everybody all at the same time. It takes time to spread. There's a parallel there, unfortunately, with what we're talking about today. So, all right. So what I want to do to illustrate that, I want to walk you through how Langer Hawke delivers a project. It doesn't actually matter what project it is or in which sector. We do this every single time. The first thing you must have, and this will be a Captain Obvious for you. Apologies for that. I have a 9-year-old. Whenever I ask him to do something or explain something to him that he thinks is so obvious that it's just, duh, Dad, he calls that a Captain Obvious with a huge roll of his eyes. So this is a Captain Obvious for us. You must have a digital model of the asset that you're building. Doesn't matter if it's a road, a railway line, a concrete slab, a shed for trains, building, whatever you like, right? Must have a digital model. It is the single source of truth upon which everything else depends. So you call an integrated model before, we call it a federated model. Must have a digital model. So this is a montage of the digital model for a big rail maintenance shed in Ipswich in Brisbane, overlaid on the actual thing. And it is millimetre accurate, as it should be, right? So we use, the thing in the middle there is the digital model for the slab in the middle of the Wheatstone, the compressor deck slab. So we use it for logistics, for shop drawings, for generating IFC documentation, for work packages, for construction planning, for scheduling, for cost. You change something, it changes the schedule and the cost in real time, for sequencing, and a whole bunch of other stuff. Sustainability model overflows that don't work very well but will eventually. Asset optimization and maintenance, right? Must have a digital model. If you do not, you will not have business in 10 years' time. Here's an example. So this Bayswater is one of these, they call them grade separations here, but it's basically removing level crossings. There's a huge program of work across Melbourne to do that. This is the digital model for Bayswater, viewed from underneath. So here's a tip from a contractor. Most of our risk is in the ground. Most contractors lose money in the ground or make it in the ground. So the digital model here is much, much more complex for the underground services. And the first time we did this, we wrote a little clash detection algorithm for a job, not this job, but one in Sydney that was all underground services. And so it goes hot pink if there's a high voltage cable running through a sewer pit, stuff like that, right? The entire screen went pink for the model, the entire screen. Thanks, designers, that was a cracking job. So that is just another example of why we do this. But the main reason for us, there's two in fact. Number one, it delivers value, right? It de-risks us. That's where we make or lose money. Number two is this. I don't have this guy's permission. I don't know who this guy is. He came into one of our community engagement days on this project. I don't have his permission to show you his face today, but I'm using the Oral-B defense. You remember the Oral-B TV commercials, if you're old enough? This man is a dentist, we can't show you his face on TV, right? So it's the Oral-B defense, I'm all good here. It's held up in the High Court. You can ask Peter Dutton, he'll tell you. He came in with his walking stick at 11 o'clock on a Saturday morning, and he was cranky, right? He was cranky. So that's Jared, and Jared sat him down, and this was one of our really early prototypes. This photo is 5 years old now. I put him in an Oculus Rift, which is a virtual reality headset, really early version. It's horrible. The early ones made you really dizzy. People passed out and fell over. Some people were sick. They're terrible. He sat in here, and Jared used an Xbox controller and just walked him through the project, up and down the stations, jumped him on the train, went to the next one, came back. You do it all virtually, right? And at about the 3-hour mark, he grabbed the controller out of Jared's hand and started doing it himself. Eventually, it turned out he lived across the road. He lived across the road, and he was worried about his view. So we actually took him in the model to his front steps. And he was able to see that actually it wasn't worse, it was better. And then he walked away without his walking stick, didn't need it, turned out. Happy as could be, right? This is the number one reason why we do this. Stakeholder engagement, right? That is where most of our risk is, whether it's a politician. Did you see the photographs of the politician who was unnamed for Western Sydney Airport? There's a photograph in the paper on the Brownfield site holding the plans, and they were upside down, right, in the photograph. So you can do stuff with this around stakeholder engagement. It's the number one stuff for us. So I want to show you the most complex digital model I've ever worked on. This is it. I don't have permission to show you, to tell you which project it is, but we're okay because none of you will actually recognize which project it is from the model. This was made more, hopefully this works, fantastic. So this is the gamified version of the model. You're not going to be able to tell which project it is, so we're okay. This was made much more complex by the fact that it was an existing asset, right? Don't tell the Sydney Opera House Trust, I'll get into trouble. Was an existing asset, so you have to do the whole scan thing. It's an incredibly complex building that there were no sort of as-built plans for. We found hidden rooms buried in basements in this building that were just boxed off, because when they were building it, they were like, oh, bollocks, how do you do this? I know, we'll just box it off, nobody will ever ask. Don't ask, don't tell, right? Absolutely extraordinary. So you can see some of the scan data coming out here, the point cloud as well. Anyway, the most complex model, and we're building a nuclear power station at the moment, and the nuclear power station, this is a piece of cake compared with this. All right, and I just want to show you really quickly a couple of things that we're doing now with our, it's called mixed reality. So what happens when you have virtual reality is human immersion in a digital world, and then there's augmented reality, which is a digital overlay on top of the real world. So when you have those two together, you have mixed reality. So these are some shots from our new commercial office, our new headquarters in Australia in North Sydney. We're using a HoloLens. It's a Microsoft product. I quite like it because it's untethered, doesn't have the cables, but it's a bit heavy. It gives you a headache after a couple of hours. So we did this for the developer. You want to rent the 23rd floor. This is actually what your view profile looks like. This is what the sun does during the day. Like it's pretty good actually. So that's for that. There's another one there for Brisbane Airport as a client where we did pre-certification of the finished product in the digital environment, so that the certifier didn't have to come to site at the end, and the certifiers were happy with that. So I'll skip on. And then this is a little. I don't normally show these. These are. Our Langerock's Innovation Centre is in Sydney, in fact. We run innovation for the entire group around the world in Australia, and there's a bunch of reasons for that, including access to talent. This is one of our internal prototyping videos. So this is a reality capture product for one of the floors, looking at tolerances for, in this case, structural elements. So we run a scanner, and then it has to be millimeter accurate, and what we're trying to do here is put surveyors out of business, in fact. I'm pretty sure we're there with that. Just don't tell any of them. Anyway, the guys on the project site really crack the shits with that, because what happens is when it's out of tolerance from where it's supposed to be, it shows up red in the model. So we did one floor, all the columns were out of whack, and of course they weren't, right? Even though they were, but they weren't. So we had to, information is power, but there are lots of cultural challenges about some of this stuff. So again, Warwick talking before about, it's basically change management, and change is hard. And technology is not the answer there, it's people are the answer. All right, how are we going? We doing okay? Okay, great. First thing you must have a digital model of the thing that you're building. Doesn't matter, road, railway line, building, school, hospital, whatever, right? Once you've got the digital model, then what we do is we use a off-site manufacturing methodology. The one we use is called Design for Manufacture and Assembly. It is not ours. We didn't develop it. We didn't do anything with it. We stole it in the time-honored tradition, and we stole it from aerospace. Right. So this is a construction methodology, manufacturing methodology that comes from aerospace. So here is this is how it works. This slide is from Boeing. There is an entirely equivalent slide from Airbus. But I use the Boeing slide because the trailing wing edges are actually manufactured in a top secret factory just over there, which nobody's supposed to know about, but has a gigantic Boeing written on the side of the warehouse. So cannot tell you what we had to sign to get in there to have a look. It was extraordinary. So, and this is the way it works. You have a full digital model of your asset, right? You break it up into chunks. And then you outsource the supply of those chunks, the manufacture of those chunks, to your global supply chain, whoever has the best availability, best price, best quality, best whatever, right? And then you bring them together and you assemble them in a central location. In this case, the Boeing factory is in Everett, in Seattle. It is the biggest building by volume in the world. Airbus does their assembly in an equivalently large shed in Marseille, in the south of France, right? So this is what it looks like when you apply that model to a building, for example. What we're looking at here, that's the square mile of London, the banking district, the financial district, square mile of London. We're looking at the one in the middle there that looks like a cheese grater. Yeah, it's called the Leadenhall building, but everybody in London calls it the cheese grater, obviously. It was designed by a Starchitect. Do you know what I mean by a Starchitect? That is an architect who is so famous that the sun goes around them. They're a Starchitect. In this case, Lord Rogers. Lord Rogers absolutely cracks the shits when you call this building the cheese grater. So every Australian at Langerock calls it the cheese grater, because that is how the world works. You've got the Gherkin in front. That was a Lord Foster's design building. The walkie-talkie is the one with the one on the left-hand side with the concave thing. That's the one that melts cars. Like, who knew you're going to build a mirror thing that's going to focus sun and it's going to... And then the shard, which you can't see, is just across the river on the far left-hand side in Bermondsey, right? That's the tall one. So all Starchitect design buildings. This is the, going to work, excellent. This is the digital model that we developed for the bid for this project. I'm going to try and run it a couple of times. I just want to show you the first grab of this video. So there was no wet concrete poured on this job above the jump form, right? And in fact, the basement slabs were also prefabricated. No wet concrete poured on the job. So if you're not waiting for concrete to set, what is your critical path? Give you a hint. How many tower cranes are there on that job? Right? So it's not concrete setting, it's hook time, right? So hook time is your critical path. So you deal with hook time by having multiple tower cranes. A really interesting story. Langeroog has its own plant company. It's called Select, the largest supplier of tower cranes in Europe. So all of those are ours, but we also did the ones for all of the buildings nearby, including the shard, which we didn't build. The crane on the top of the shard that was left, the last crane that came down, the driver for that took photographs every day and secretly uploaded them to Instagram. Of the sunsets and it's extraordinary. He had more followers than Kim Kardashian at his peak. It was extraordinary stuff. So the issue is hook time, right? So that is why you have multiple tower cranes. In that case, there were 5 on that job. Compare it with any job in Australia where you have 1, sometimes you have 2, right? Just a fundamentally different way of delivering a project. The factory that built that building is this. So that is Langeroog's primary manufacturing facility for concrete products in the UK. It's called Explorer Manufacturing. It has robotic steel cutters and benders for all of the rebar, 3 automated manufacturing lines. That photograph is very old, it's about 10 years old now. It is much busier and bigger than it is in this picture. But every job that Langeroog does in the UK that involves concrete comes out of that factory. We turn away work that we can't deliver in this way. Right? So that is where we are with our business in the UK. And we're about 5 years ahead there than we are in our Australian business. Of course, this is in the geographic centre of the UK. It's in between Nottingham and Sheffield in the Midlands. So it's 200 miles to Manchester, 200 miles to London. Of course, if you apply that model in Australia, you've got a factory in Alice Springs and a couple of really bemused kangaroos. But it does actually work because you can put it in Asia, Thailand, and ship it down the main shipping channels. Right? So most of our modular stuff in Oz gets done from an Asian supply chain. And we get asked a lot, quantify the benefits. Is it better? How is it better? So we finally had an opportunity to do that recently. There's a project in London called Crossrail. It's the new Trans-London railway line. It's the biggest construction project in Europe for the last 10 years. We have a whole bunch of station fit-out packages, including 2 right next to each other, Liverpool Street and Tottenham Court Road. And we got permission from the client. Crossrail was a fantastic client, really interested in innovation, and they said, let's do a compare and contrast. So the Liverpool Street we did with DFMA, and Tottenham Court Road was a traditional in situ cast and pour, both 40 metres underground, accessed by a single shaft with a single tower crane, and you've only got 50% of the time of the crane because the other 50% is used by other contractors. But you never get winded off because you're underground, so it kind of makes it up, right? So the DFMA methodology, 30 weeks, 7 people, plus about 8 more in the factory. But that was the installation crew. The in situ, 41 weeks, 57 people, right? This is another Captain Obvious once you see it like this. And I'm not allowed to tell you the financial information, but you have a guess. The Liverpool Street people are smiling. The people on Tottenham Court Road are not smiling. So again, some challenges. We had to develop our own suites of specialist installation equipment using straddle carrier, automated straddle carrier technology, because you getting stuff down shafts, and we make these things up to get these dropped into place. So I've got a couple of build shots. So I've got one build shot. There you go. I'm not finished with DFMA yet. I want to share some more examples. This one's from Australia. Darlington is that's the old Mitsubishi factory in the top there. It's a Southern City bypass for Adelaide. This is the single most awesome thing I've ever worked on in my career, just so you know. So there's 4 bridges here that needed to be constructed. So there's the digital model. So there's a GIS underlay with the BIM model, if you like. We don't like BIM. What if you're building an airport? Is it called airport information modeling then, or is it road information modeling? Is that RIM? Like, how does it work, right? So we just call it digital engineering. We call it digital engineering. So this is the digital engineering platform and model. And what we did DFMA bridges here. So the longest of these was 180 meters long, and it weighed about 3,400 tons. So it's longer than the Adelaide Oval, and there are 4 of them. So it got constructed in a bunch of factories around Australia, mainly in Adelaide, and then it was assembled in a paddock 2 kilometres away, and then it walked itself into place. And it was incredibly complex, doing a 3-point turn with a bridge. You might think it wasn't so bad, right? So we had to hire a physicist to do sort of motion paths and pivot locations and a whole bunch of stuff. And we work with Sarans, who are an SPMT, self-propelled modular transporters. The big, I'll show you a picture in a sec. Sarans were great and did a really good job here. So there you go. There's a DFMA bridge. This was the little one. And you can see it's sort of wiggling itself into place. It was actually a 12-point turn in the end. And the other thing about this bridge is this is the most intelligent bridge. I'm pretty sure it's the most intelligent structure, certainly in Australia, probably in the world. It was instrumented with every sensor money could buy and a whole bunch of stuff money couldn't buy that we had to make, because the loads in transit are much greater than the loads in situ. So we had to make sure it wasn't damaging itself. So we allocated a 72-hour window to get it to move the 1.6 kilometres down the road to get it into place. And at the end, it was jogging, right? The guy with the kill switch. So it was fully automated, but there was an operator with a master switch who could have stopped it from moving. He was jogging to keep up with it. It was going so quick, and it was in 11 hours. We don't normally like being on the front page of the newspaper. There's a BP garage across the road here, and people pulled their camping chairs out and camped overnight to watch it as it went. And then it was on the front page of the advertiser. Very, very cool. So there are 4 of these. We've done 2. There's one going in this weekend, in fact, and then another one 2 weeks' time. So if you want something really exciting to do this weekend, get yourself down to Adelaide, get a camping chair from Bunnings, pitch up to the BP forecourt, and you can watch what's going on. All right. You must have a digital model. Once you have a digital model, you can use different delivery methodology. In our case, design for manufacture and assembly. And that can extend to design for manufacture, assembly, disassembly, recycle, reuse. There's a whole bunch of stuff you can do with that. Once you have those 2 things, then you can start using and exploring different manufacturing technologies. Right? Anyone seen this? This is a very famous car. Seen this car before? Yeah, good. It's the world's first 3D printed car. Right? It's designed by a little company called Locomotors. This is from 2014. Got a couple of pictures of the build going on. Does anyone own a 3D printer? Use one before? Yeah. You can buy them from Officeworks now, right? That pretty much tells me that technology adoption curve, we're right down where the laggards are, if Officeworks sells them. The way they work, you've got like an old dot matrix printer, layer by layer, and the 3rd dimension gets built up as you put the layers down. This printer's quite a big one for a 3D printer, but it prints Lego. So this car is actually made from ABS plastic. It's a Lego car. So you see how it goes. It's a bit quirky looking, but that's okay. Then they added all the substructure in, the electrics, drivetrain, that sort of stuff. And then they drove it down the red carpet. Right? Very, very cool. So Locomotors are a startup. If you order one today, that's what they tell you you're going to get. Now the whole point about this, right, is that anything you see there is customizable for free, right? If you want, I don't know, cow horns on the front and wings on the back, right? If you can draw it, they can print it. If they can print it, it's free. It's known as mass customization, right? Mass customization. That is the power of 3D printers, right? Now, of course, because they're a startup, if anyone's been involved with startups, this will be hilarious. The rest of you work with me here. You order that, right? It's about $30,000 US. It's the same price as a Mini. That's what you get. So they discovered that not a lot of people wanted to order that yet because that just wasn't right yet. When you can order a Mini in the US for $15,000, why would you order one that looks like a Mini for $30,000? So price is key here. So what they decided to do was make these little autonomous. So this is now an autonomous vehicle. It's got a little slam system on top, but you can have a look at the front fender. It's still the same printed material, right? It's the same substructure, I think there's one at Houston Airport that takes people between the terminals, so you can see them in use. Locomotives is somewhere in the Midwest there. Right, some other examples of 3D printed structures. This one from Airbus. I love Airbus. They have an extraordinary innovation lab just outside of Paris, where they do all sorts of stuff. So, if you want to know where the future is coming from, look outside of your own industry. We get lots of inspiration from aerospace, automotive, Formula One in particular. This is from Airbus's innovation lab, AP Works. The motorcycle frame there is 3D printed. It's a titanium printed frame. And it's really interesting. It uses a concept known as generative design. So in this particular case, you start out with a solid digital block of titanium, and you take out a chunk, run a finite element model over it, take out another chunk, run it again, another chunk, run it again, run it again, until you get the minimum quantity of material that gives you the structural performance that you're after, or the mechanical performance or the electrical performance, whatever you want, right? The thing about generative design is you always end up with something that looks like it's come out of the Alien movies. So I'm not sure the world's ready for that yet, and nor was BMW. So here's BMW's version of the same thing, this one from earlier this year, and all they've done, any mathematicians in the room? That's so disappointing. My number one tip for you if you want to do innovation, go and hire a mathematician. They're gold. They're unloved. They're just looking for a friend, and they do absolutely amazing work, right? So all the mathematicians, the boffins at BMW have done here is they've changed the boundary conditions and made it more rectilinear, so it looks more. If you can say sexy in a German voice, it looks more sexy, right? That's where we're going with this. So again, some work from my other life. These are 3D printed body parts. So apologies for this. These are a bit icky. The way this works, stem cells are extraordinary little critters. You can tune them to become whatever it is you want them to become. In this particular case, you're after skin. So these are comparatively simple things with cartilage in them, so ears or noses, right? But do you remember the Time magazine article with a mouse with a human ear growing on the back? It's not very long ago, 10 years. It's completely redundant, right? You just print the scaffold now, dunk it in stem cells, your stem cells, and you grow your skin. And then back she goes, right? Right. So my point here is, if you can 3D print body parts, why are we not doing, or cars, why are we not using 3D printers in construction and manufacturing, right? And the answer is we are. So this is Langer O'Rourke's version. This is Bessie. Bessie is the world's largest 3D printer, at least she was when she was built. She's 30 meters long, 12 meters wide, 6 meters high. Bessie can print anything you want, including buildings. Sorry, I get asked a lot, why is the robot called Bessie? And it's really important that all robots should have a name, because when they take over, you need to know what to call them. Right? So what we did with Bessie, we didn't go out to print a building. We actually just found a little niche for her in an existing supply chain, and we made Bessie make molds. So we're back to Crossrail again. Those two stations I showed you before, there are all these underground pedestrian tunnels. There was a run on glass fibre reinforced concrete in the UK at the time. So you couldn't buy a mould to cast them to save your life. So the price quadrupled almost overnight. So instead of being £4,000 a mould, they were £12,000 a mould. Bessie can print a mould for about 400 quid. And instead of taking 12 weeks, it takes 8 hours, right? So it's just-in-time delivery. So that was what it was designed for. We have a little GRC factory in the UK. This is the first one ever being done. And you get these sort of, and it works because these are double curvature panels. So I think for our packages of Crossrail stations, we had 95,000 unique panels that needed to be done. and you can see what it looks like when it goes into place, those curvy ones. And here's a couple of the build sequences again. How are we going for time? We doing okay? Okay. So you can see what it looked like. So Tottenham Court Road is now open, Liverpool Street's open. If you're next in London, you can go and see this stuff. So that's what it looked like before it was open to the public. So, and that's the latest piece of work we've done with Bessie. We're doing some metals. So metal printing has come along in leaps and bounds in the last little while. For you folks who have a sort of an MEP interest, Airbus again, they print the wiring looms in the A380s, right? Have done for 10 years. They don't run cable anymore. That's just dumb, right? They 3D print them. So, it's coming. Right, digital model, different delivery methodology, different manufacturing tools. When you've got all those things, then the thing that you make needs to be intelligent, right? So, I don't know, if a bus driver falls asleep and crashes into one of the columns at the front of this building, the building doesn't know it's been hit, doesn't know if it's damaged, doesn't know how badly damaged it is, just has no idea about that stuff, right? But if you cut your finger on a piece of paper, you know you've been cut, you know if it's bad or not, you know if you need to go to hospital or not, or get a Band-Aid, and you self-repair, right? So why doesn't a building do any of those things? And the first answer is data. It doesn't have the analytic capability. So this is a lovely piece of work that's come out of the University of Cambridge. That's the foundations for the Sir Francis Crick Institute. It's in the north of London. King's Cross is just across to the right-hand side. That's St Pancras Station, where the Eurostar goes from. And what the clever cookies at Cambridge have done is they've come up with a technique to assess the performance of any structural element here by running light through optical fibre that's attached to it. So it was pioneered in the tunnels for the London Underground and on bridges in the UK. We did it here. And the standard methodology for structural performance for piles is that blue thing that you see there on the right-hand side. It's called an Osterberg cell. Costs you £150,000, has a car battery in it. When it's buried in the concrete in the ground. When the battery dies, you stop getting data, right? It's a single point data. With optical fibre, you're getting information at a really granular level from all of these. But you had to do some incredibly complicated maths to make this work. Again, maths, right? Go and find a mathematician, give them a bit of love, they will pay you back in spades. So turns out on this basement, when designers design foundations, right? When I'm a chemical engineer and I design an oil rig, my design factor, my fudge factor is about 10. That's because it's so uncertain, I just multiply everything by 10 to make sure I'm safe, right? In geotech, it's even more than that because we've just got no idea what's going on the ground. But I am now measuring in real time over the life of this asset the performance of these foundations, and I can tell you that I only need every second one of those columns. And I'm happy to give you a performance guarantee now because I absolutely know, right? Imagine if every element of the building was doing that. Here's another example. Again, it's a heavy civils example. This is Thames Tideway. It's the new super sewer in London. That is one of the most impressive holes I've ever seen. This is one of the access shafts. There are multiple ones of these going along the Thames. To give you an idea of scale, the excavator in the bottom of that you can kind of see is the biggest excavator money can buy, right? And there are 3 of them down there digging away, trying to get this thing down. The reinforcement cage on the outside of this is instrumented with optical fibre again. So as you see that graph on the right-hand side, you've got 3 red dots joined by a dashed line. Those are Osterberg cells. And so when the engineer looked at this, he said, well, look, do you know what? That outlier right on the far right, that's obviously not right. There's obviously a problem there. With the instrument, we're just going to ignore it. So we're going to draw a straight line between 2 points. Yes, we're good, right? But the optical fibre, you can see, is the really granular black circles. And what it's saying is, do you know what? The reinforcement in that location is not good. It's not good. And the engineer made the contractors go back in, cut the concrete away, assess the reinforcement, and we found a big problem, right? A big problem, and then it was redone properly, right? So this is what I think of as a company killer. Can you imagine in 15 years' time, there's suddenly a massive hole appear in one of these shafts, and London sewage suddenly pours out all over the place. You don't recover from that, right? That's the equivalent of the Banking Royal Commission for us, which we don't want, right? Which we don't want. So this is why this stuff is important for us. The challenge is you get so much data that you've got an analysis problem. So then we're into the realm of, once your asset is giving you information, then you've got to analyze it. So this is known as big data. People call it big data. I'm not a fan of that phrase. We prefer massive analytics and artificial intelligence. Give you an idea of what that looks like. That picture, that's all the email traffic inside Laing O'Rourke for 1 week, January 3 years ago, right? Color-coded by project. And what we were doing here, the hypothesis here, that's known as a social network. This is called social network analytics. It's a type of big data analytics. We're looking at profitability. I'm trying to find which projects will be profitable and which ones will be, everything we do is profitable, obviously. Which ones will be less profitable, right? So to give you an idea, blue is head office, the dark blue in the middle. Green is the most profitable project ever in the history of Laing O'Rourke. And this is about connectedness. So again, to mathematicians, how many of you remember eigenvalues and eigenvectors from first year calculus when you were at uni being engineers? This uses eigenvectors, right? And it's looking at connectedness. The mustard yellow project down the bottom that has very poor connectedness is still in court, right? That's also a very positive proxy for profitability, inverse correlation with profitability. Here's an example. This one's for civil engineering again. This is from the Woolgoolga to Ballina completion of the Pacific Highway up in northern New South Wales. That's basically a 200-kilometre project with, I can never remember, and I'll have this completely wrong, but it's many millions of tonnes of cut and fill, right? And the profit driver for this project is how you balance cut and fill across 200 kilometres, right? So that is the perfect thing to do big data analytics. What we did here was looking at fill compaction and the apologies, I need a coffee. Efficacy of fill compaction, right? So what the guys have done is they've all of this Caterpillar equipment comes ready to be fully autonomous. Does anyone own a Tesla? Got a Tesla? Your Tesla can drive fully autonomous at the moment, level 4, right? They just don't turn it on. The Cat machines are almost the same. So what we've done here is a Goldilocks map, and here's another really powerful lesson for us around robotics, automation, and artificial intelligence. What we're doing here is we're measuring compaction efficiency in real time. So the standard way of doing it is you compact over it. A week later, a guy comes with a probe, surveyor comes along and says, nah or yeah, and puts a tick in a box and comes back a week later, and you monitor it over a couple of years to make sure the settlement works out. We're actually doing that in real time. It's just a little accelerometer chip in the thing. So this is a Goldilocks map, the guys call it. What you want is green, blue is too much, red is not enough, right? And what you see here, humans, in this case compactor drivers, have a tendency to show biases about where they like to drive. Who knew humans had biases? So there are some parts that they just like to go over a lot, and some parts they only like to go over a little bit, right? It means you're not getting very good compaction. And so what the answer is, you just go over them a lot more than you need to. So if we had this technology across the entire 200-kilometre project, I'm pretty sure we could pull up about $1.3 billion out of the job. For example, if the compactors were automated, which they could be. I'll talk about that in a sec. All right, so that gets us on to robotics, automation, computer vision. Actually, that's around the wrong way. Before you have a robot, and before you have automation, you must have computers that see. If you don't have a computer that sees, what you've got is a remote-controlled car, right? That doesn't really help you. So when everybody thinks about robotics, automation, they think about drones. This is one, again, a project I'm not allowed to name, but you can see the guy in fatigues in the top left-hand corner. It's the only time I've ever been shot at on a Laing O'Rourke project. It's really interesting. So, who knew drones were not allowed above Air Force bases? No idea. So what you can do with drones, this is pretty standard stuff. This is an assessment of cut and fill volumes. So I think it's an Autodesk product, but there are a whole bunch of them, platforms that do this now. When we first started looking at drones 6 years ago, there were 2 drone companies in Australia. There was Skycatch, which is a Google funded American company, and the little startup in Sydney called Propeller Aerobotics, who do great work, who are still going. The Skycatch drone was doing some work in Western Australia and flew into the side of an active oil and gas facility and exploded. And then there was one drone company in Australia, right? Today you can find them in the yellow pages. And we stopped counting when we got to 200. It's a commodity service now, right? I need a drone. I can ring somebody up. I'll have the data by the afternoon. That's the rate of progress. When we talk about robotics automation, we're talking about autonomous vehicles, because that's more interesting for us. So I have no way of scrolling through this. What we did here was a demo a couple of years ago that's a water truck, and it was a bog standard water truck that is what you would buy from the shop. Needs a driver, has pedals, and we automated it. It took us about 6 hours to turn it into a fully autonomous water truck, using some gear from a US company called ASI. So it basically puts mechanico servo things on the steering wheel and on the pedals. And then there's, you can kind of see Russ in had to have a safety driver. So Russ sat in the middle seat with his arms crossed. He was deeply uncomfortable. Every time because we programmed it to do figure eights, every time it started to turn, he went to reach for the wheel. In the end, he got comfortable enough, he moved into the passenger seat, and we did that. So you can see him there in that, right? So this is actually pretty dull stuff. And I show you this to say just how easy it is to do this now, right? I'm more interested in this. So this is what happens when you have computer vision systems on autonomous vehicles. This is a screen grab from Google. It's what the Google driverless car sees. So on the top of the car is a thing called a SLAM system, simultaneous location and mapping. And what it does is it assesses everything that it sees in real time and works out its vectors, so position and velocity and trajectory, right? And then it puts that in a little purple box. And so if it's a family of ducks crossing the road, or a kid with a ball, or grandma with a Zimmer frame, like, it assesses all of those in real time, and then it feeds that back to the software, and it works out, I need to brake, I can go round, whatever it is, right? Yeah. So again, this is one of our the problem I have is that the SLAM system costs more than the car that it's on, which is no good. I got 200,000 bits of plant around the world. I can't put one of those on every bit of it. It's not going to go. So we had to build our own, a nice cheap one. So this, I don't normally show this. This is our internal prototyping video again, when we developed our own SLAM system with the AI that recognizes, AI's artificial intelligence recognizes what it's seeing. And the reason I don't show this is because the artificial intelligence, when it's learning, it starts out like a newborn baby, and then it's a toddler, and then it's a teenager, and it finally grows up, right? So the AI that we developed when it was a newborn baby and a toddler, it was a bit racist. It's a bit embarrassing. So what you see here is Alex. That's Alex. He wrote some of this code, and he worked with Suket, who has Sri Lankan heritage. And all we're trying to do here is tell the difference between a human and a chair. This is our office in Sydney, our innovation lab, right? Just want to tell the difference between a human and a chair. So it sees Alex, and it's like, yep, I recognize Alex. And then Suket, because his skin's a little bit darker, it's like, not happy with that. And then it's a chair and Alex and Suket, right? And it's what you're seeing here is it's learning, okay? And it takes about 5 minutes, but it eventually gets happy. And it's able to work out that that's a person, and that's a chair. And chairs are not a threat, they don't move, so I don't need to worry about that. I just need to worry about the two moving people, right? So we got there in the end. And then you can do stuff like this, right? So this is a camera in our storeroom at the office. We have an issue with somebody stealing biscuits from our storeroom in the office. So we whacked in the camera to find out who it was. And we made the camera detect if you were wearing the right PPE or not. So it could detect if you were wearing safety vest or otherwise. So this is Rod. Rod turns out to be our biscuit thief. But Rod worked it out. If he's wearing the high-vis vest, then he's okay. He can go in and steal the biscuits. The fact that Rod is wearing board shorts and a pair of thongs, like we haven't done feet yet, so easy, right? So this is a way ago now. This was the first live prototype of this system on a real project after it had all grown up. So all you're doing here, apologies, this is a bit Blair Witch Project, so it's a bit jerky, but the camera is on a laptop. We're just pivoting left to right on the laptop. And what we're doing here, this is a live rail job in Sydney, so we're looking for incursions into the rail corridor, right? And by this time, the AI in here can recognize people, plant, and other equipment, right? So plant is in blue if it's in the right place. So that's an excavator. If the excavator boom is over the railway line, then it shows up in red and it sends an alert to the safety officer for the project because that's bad, right? What we're doing here is we're looking for people who are not supposed to be where they are, including, can you see the guy hiding in the electrical cupboard? Yeah, so I can because I know he's there, and I've seen this video a bit, and you can see it on the screenshot on the bottom as well, right? It's seeing the shoulder, the left shoulder, and a bit of the back, and is able to recognize that is a person, B, somewhere they're not supposed to be, that puts them in danger, right? So that's what you can do with this. So this is, again, another one of our internal videos that I don't normally show, but just for fun. That's Ben. Please disregard the fact that Ben is walking like a creepy man and has an Ed Kelly beard. Ben wrote the AI here. What we're doing now, the light around the hat's called a halo light, and we're hooking in the sensors from that robot with a human, so that it's giving you different ways of alerting you to hazards. So if you walk behind an excavator that's backing back and you're at night in a dark zone, you can't see it, your light starts to flash. Right, it's just simple things like that. We've also got alert where if you have a Fitbit or an Apple Watch, it vibrates, all that sort of stuff, right? That's where it is today. This we call this Tech Toolbox Spotter. It's a robotic vision safety system. It's just about to be spun out, and we've done sort of lots and lots of assessment on it. One of our customers, when we took it to site, said, "Well, that's all and good for people and plant, but we have a problem with dogs. We have a problem with dogs on the site. Can it detect a dog?" So we were pretty sure it could. And in fact, that's Barrels. Barrels is our office Groodle. We have a puppy in the office. And that's Ben sitting on the chair. So you'll see that it's more confident that Barrels is a dog than it is that Ben is a human. Which, if you've met Ben, is a pretty fair call, actually. So I make fun of my robotics team. They're all incredibly smart mathematicians and mechatronic engineers, and they do amazing stuff. So when you see Toolbox Spotter as an independent platform spun out of Langer Rourke, you'll know where it's come from. So the other thing we get with robotics is, the whole Iron Man thing. And this is a piece of work from Hyundai. They actively have said it was inspired by Iron Man. And I'm really interested in this, but this comes back again to psychology and biases in humans. So what do you think happens if you give a macho bloke in a macho industry an exoskeleton that lets him lift half a ton? Right? You're going to have car flipping competitions is what you're going to have. And that is not the right answer. Also, in real life, that's what it is. And it's utter rubbish. So this is Will. Will's one of Bright Young Things. He has a PhD in maths, you'll be unsurprised to hear. And after this video is taken, this is not a Hyundai product, it's from a different, in this case, Japanese robotics manufacturer. It started to malfunction and started making Will do like squats and stuff. It was genuinely awful. It was horrible technology. This stuff is much better. These are non-powered exoskeletons. So they support you for single tasks, or they might hold a tool in the right place while you're working at heights, for example. So that, on the right-hand side there, this is Jin. He's one of our interns. He's come across from Stanford. That little bit of cast FRP structural beam weighs 50 kilos. And Jin is lifting that with his pinky because the lifting arm there just has a whole bunch of hydraulics that help you do that. So it could hold a rivet gun at heights, right? And you don't get RSI. Again, this idea has come straight from Airbus. We've just shamelessly borrowed it because it's great. So there are 3 US startups that have all come from University of California, Berkeley, that have these different exoskeleton technologies. All right, so we're almost done. So what happens when all of that stuff is brought together, right? So I get asked a lot, is it giant 3D printers printing buildings? And I don't think it is, actually. It's micro, not macro. So this is an amazing piece of work from the University of Pennsylvania, using a digital model, DFMA methodology, and then robotics to assemble a structure. So don't get hung up on the fact here that they're cheating a bit because there are magnets on the end, right, and they click into place. There isn't an army of PhD students behind that curtain with joysticks moving these things around. This is fully autonomous. It plans in real time. If there's a bit in the way, it reprograms, right? What they did here is they solved the maths. Back there again, hey? They solved the maths for swarm theory. You know when bait balls move or birds swarm, they never run into each other? So they've done the same thing and they've coded that into these drones. Turns out it's really simple. You just maintain a fixed position in 7 directions, and that's how they don't knock each other. For years I thought it was pressure, but it was much more simple than that. So a lesson there about nature. I'll play that again, right? So this is the future from our perspective. You will have shipping containers full of manufactured products that get delivered to site and are assembled in near silence over 24 hours using a digital federated model. I can absolutely see this coming. Right? So when I did this first for Langerook's board and strategy board, they were like, Andrew, that's that's great. It's a little bit science fiction-y. Thanks very much. Don't let the door hit you in the arse on the way out. And I said, well, hang on, I've got a couple of examples for you, right? Because the thing about disruption, it never comes from within. Never comes from within, right? Ever. Never, ever comes from without. So here's one from Google. Google building a new headquarters, committed to do it in Mountain View in California, their global headquarters. It was designed by another star architect. Remember them? This one has this weird, funky roof. So Thomas Heatherwick is a British architect, and the Danish firm BIG. And they did a market sounding to get prices from the contractors, and the American tier ones were like, you beauty, this is going to be great. And their numbers came back in, and they were eye-watering, even for Google, right? And Google said, you know what? There's got to be a better way. And in the space of about 3 months, they came up with this concept called a crabot. Crabot, half crane, half robot, crabot, right? And they have prototyped it, patented it, and have committed to use it for the internal fit-out and construction of their building. No tier 1 contractor in sight. Right? Don't need them. You're extinct. So that photograph comes from Business Insider. I just downloaded it from the web. You don't need to take a picture of it. You can find it really easily. Type in crabot. Right. So then we're getting on to this concept about the future of work. What does my job look like in the future? The robot ate my job. That sort of stuff. Right. So there's a lovely study, very famous study called by Frey and Osborne, who are 2 professors at Oxford who studied the US labour market and looked at the impact of what they've called computerization. So computer is artificial intelligence, robotics, automation, all of that stuff together on jobs of today, right? And they do that by taking every single job and breaking it up into tasks, and then looking at the probability that each of those categories of tasks will get automated, right? So that the study's been around for a while. The Centre for Economic Development in Australia, CEDA, did an Australian version of that last year. And these are the results, right? Turns out there are a whole bunch of manual labour tasks that are really difficult to automate. I think you can tell by looking at me that I spend hours on my personal appearance. And I have a really important relationship with my hairdresser, Frank. And we spend hours each day getting my hair looking just like this, right? It turns out it's almost impossible to get a robot to cut hair. And if you can, nobody wants it, right? Yeah. But the other side of that is also flipping hamburgers. Really difficult to do with a robot, right? The other side of that is if you're a paralegal or a lawyer and your job is to assemble case law and structure arguments, there is an AI that does that today better than you could ever do it. Faster, cheaper, better. Never misses a case, right? Or if you're a surgeon, if you're a man of a certain age and you have an issue with your prostate, right? Happens to all of us. You want that surgery done by a robot. Look at the data. You do not want a human surgeon doing that surgery, right? Also orthopedics, shoulders, knees, hips, right? You want that done by a robot. They're better. So you have this bimodal distribution, white collar and blue collar jobs, right? Now the key here, the key to a future-proof job is to have a deeply creative element to it. So in spite of the fact that it sounds a bit silly, hairdressing has a deeply creative element to it. right? Creativity, at the moment, we cannot automate, which is why I get the shits with universities, because the way we educate kids today beats the creativity out of them, right? They start out singing and dancing and drawing and running around and playing. They're like, no, do your homework. Like, it's just not right. So if you want to keep your job in future, because engineering used to be about deep creativity, and we need to go back to that now. It shouldn't be STEM. You know what STEM means? Science, technology, engineering, maths. It should be STEAM. It needs to be arts in there, right? It's that, got to balance both halves of your brain. So here, this is what it looks like. It's one of the examples. This is my some examples of my other life in the lab. I want to finish with some examples around biomimetics and using nature to inspire engineering. This is my favorite example. It won an Ig Nobel Prize. The Ig Nobels are the alternative Nobels for research that cannot or should not ever be repeated. That's how it works. This won the Ig Nobel Prize for sustainable transport infrastructure design. So that is a map of the Greater Tokyo subway network. It was developed largely after the Second World War, millions upon millions of man-hours, and there's another issue there about diversity, which we won't have time for today. And they think that is pretty much optimized in terms of the quantity of track that you need to get all of the people to where they want to go, right? This is slime mold. It is a unicellular organism that lives to do two things, to eat and reproduce. That's all it wants to do. Can't think, right? So what this very clever prof at the University of Tokyo did, he used slime mold to design the Tokyo Rail network, right? So what he's got is a petri dish, the shape of the bay, right? And he's put oat flakes, which is the slime mold's favorite food, where the major population centers are. And then over 26 hours, the mold does what it does. It experiments. It's like a child. It goes out, it explores, it comes back, it explores, until it's got a network that is optimized for getting to the food, right? You see what they're doing? Isn't that clever, hey? And then when you compare the actual network with the slime mold network, the actual network is over-designed by about 30%, right? So, and I've actually done this experiment. I haven't done it in Victoria, but I've done it in New South Wales. There's nobody here from Transport for New South Wales? Have to check this. They're Langerock's largest client in Australia. It'd be really embarrassing if I showed you the. Yeah, in fact, I'm not allowed to. I don't belong to our Australian business. I work in a group role, so I'm based in London. But I have to make sure that my local cousins are happy. So, as my last example, I'm almost done. I appreciate I'm running a bit over time. This is a gorgeous piece of work from the University of Delft in the Netherlands. This is about self-repairing materials, again inspired by nature. So clever folks at Delft had come up with a bacteria that, in the right conditions, poos concrete, right? So think about that for a second. That could be deeply uncomfortable. What they've done is they've got these little hairline cracks in precast concrete that are not structural, but when it rains a lot, say in a country like England, you can see you see them up. So when the sky leaks, you just see these little lines in buildings. It's no good. So what you do is you get this bug and you put it in a squirty bottle and you just squirt it in there, and it wants to get happy. So happy is dark and warm and wet. So it crawls into the crack and it gets all comfortable. And when it's comfortable, it poos. And this one, it poos calcium carbonate, right? Poos a cement. And then the crack fills in, right? So I think this is absolute gold. I love this. I managed to get permission to bring the bug in from the Netherlands into the UK. We did a trial in our factory, the one I showed you before. And it happened to be in the middle of winter, and I didn't want to go across for it. It was going to take a few weeks. So I set it up, and then I said, send me a photograph every morning. Take a picture of the crack. So 6 weeks, nothing happened. It just did not work. But they were saving money. They didn't turn the heaters on. So it turns out it needs to be warm, wet, and comfortable, not just minus 14, wet and comfortable. The minute you turn the heaters on, the crack disappeared in about 3 days. And then I went through this really long process to try and import it into Australia. I just couldn't get through the quarantine laws. So I'm like, you know what? I wonder if it's a unique bacterium or not. Turns out, in every soil anywhere in the world is something that does the same thing. So you take a bit of soil, put it in a bottle with some water, shake it up, squirt it in, it'll do the same thing, right? It's just extraordinary stuff. So I'm really glad I didn't pay a whole bunch of money to buy the IP for this, because it would have been a waste. So that's everything from me, folks. I'm all done. I hope you got something out of that. It wasn't too much for this early in the day. You have a lovely day.
Stay here for a second, fascinating is the word that comes to mind. I think from the first two presentations with Warwick and Andrew, my view on it is you've seen a real sense of authenticity to both of those, and certainly a good reason to be here, and especially if you're a surveyor. So look, we are running a little bit over time, but I don't think anyone cares. I certainly don't. We've probably got time for a couple of quick questions. We're lucky enough to have Andrew on the panel later in the day, so we'll maybe just do a couple and then keep moving. All good? All right. Fantastic. So, and I think we were pretty safe to clap at the start of your presentation too, Andrew, so thanks very much. And